Okay, well, just this maybe won't be quite part of the podcast, but just quick introduction. This is my friend Grant. I've known Grant since I was in 6th grade, and this is my friend Derek, who I've known since I graduated college.
Pleasure to meet you.
Nice to meet you. Yeah. So for the listeners, this is like actually us meeting for the first time. So
it's
not a staged meeting introduction
or organic.
Yes. Cool. And Zach, you wanted to bring Grant on to ask a question. Grant, I don't know what your background is. It's not physics. Is that right?
It's not physics. I have a bachelor's in nursing.
Okay.
Which does not require physics or even really calculus. So, I bring a question and my curiosity and my best ability to try to understand your guys' explanation.
Yeah. So quickly for the listeners, we're just trying. This is a new bit, I guess, new piece for us. Obviously, you've never heard a third voice here. And I've said this to Derek for a long time, but I've yet to commit to making it happen. So this is the first time I've made it happen that I can say I want guests on the podcast. I want to talk to other people. And so my thought here is, I've known Grant since sixth grade. I always say that word wrong. And we've just been inquisitive our entire lives. We did crazy things as kids. Like we found an old stove on the road once and took it apart, and we bought a grappling hook and tried to see what we could hang and do with a grappling hook. I don't know. We like to find something and poke and prod at it and see what happens.
Young inquisitive minds trying to explore the world to our best abilities.
And so as we got older, we kind of diverged, took different paths a little bit. But whenever we meet back up, Grant always has a question for me, because he knows I studied physics. And so he always has some sort of, how many hydrogen atoms are there in the universe? Or, why do things fall when I drop them? No, that's maybe a little too trivial. But, he always has something. And they turn into these long conversations that I think are pretty interesting. And what I like about talking with Grant is Grant's kind of on this level of where he has poked and prodded around enough in the world that he has a pretty good intuition for things, but he doesn't necessarily have all the jargon and terms and everything that you and I have, Derek. So I think he's a pretty good representative of someone we might find in our audience. So I figured having him be able to say wait, I don't know what the heck you guys just said there. Let's try it. So that's kind of the goal here. And so, I asked Grant to come up with a question. He told us ahead of time, so we had a little bit of prep time.
Yeah. Well, what actually happened is Zach said, do you have a question? And immediately in that conversation, I was like, yes, I have one. I have one cooking. I've had one for some time. So there was no need to come up with a question. One was already there.
So what's the question? Let's hear it.
So I tried to think of how to phrase this question in a good manner. Here's what I came up with. Does randomness truly exist? Or do we just not have the means to collect enough data to calculate what we call random?
Yes.
Yeah, done. See everyone. Thanks for coming, Grant.
The answer to that A or B question is yes.
And I wanted to, my interest in this question, I kind of almost don't want to go there because it could lead to philosophy, and I figure that's not really where we're trying to go. So I am just curious if things are random because it's not worth figuring out where exactly everything is, or if we're limited by computing technology to figure out, everything. Are things actually truly random?
So I'll admit, when I first heard the question, I interpreted it interpreted it totally differently than the way you asked it. I thought it was going to be a question about computer algorithms, and like if you type a rand in Excel and it gives you numbers, like is that truly random? And Zach, you and I have talked about like fancy ways that computers actually, quote unquote, actually spit out a random number through weird tricks. So that's where I thought it was going. And then after I think a little bit more of an explanation, I realized that's not what the question was asking at all. That's not at all what was intended. So, yeah.
I don't think that's out of the bounds though of what would be interesting to help Grant here understand whether randomness is real or not.
I mean, and also if the initial question is very much like, yes. I didn't know that your interpretation of my question was a question that I have, but now it's actually also a question that I have.
So in addition to that, yeah. Can computers spit out random things actually randomly? And I think we're going to eventually end up in philosophy no matter what we try to avoid. Like it's going to go there. Because as Zach said, physics, like if you just are like the laws of physics are this, and they are random, yes. And then we're done. And so we can talk about why. But I think when people ask about randomness, it's implicitly, we assume physics plus the concept, I'm going to say it, free will. I think that's where we're going. But it's like, that's outside of physics. So anything inside of physics is the randomness, yes. But outside of physics, there's other things that we can tack on and describe emergent things about people. And I don't know if that's where we're going. And I did see this question on Reddit. I don't know if you were the asker of this question on Reddit like a week ago, but the person specifically said the motivation for the question was staring at a fire pit and watching the flames and saying, if I knew everything about the molecules that produce that fire in the fire pit, would I be able to describe the flames perfectly? And then the like not being able to do that was what they meant by randomness. So I don't know if you have something to add to that, Zach.
So yeah, I have two things. One is I think my joke answer of yes though was to answer that both things that Grant talked about I think are true. That if we could know things fine-grained enough, like what that question asker was asking, then a lot of times we can kind of have determinism, like we would know what's going to happen. But if you go deep enough, particularly towards quantum mechanics, you get to the point where you have, as far as we know, true randomness. So, but both kind of exist. And I kind of listed I came up with three, physics examples of the kind of the different types. And I can talk about each one of those briefly, and we can go into detail on any one of them if you want. The three things I came up with was kind of like a thermo talk a little bit. I don't have much to say on this, but a little bit on chaos, and then some on quantum.
I think you're kind of headed in the right direction. I feel like I should preface. I feel like I should preface a little bit of my of where my question comes from and my understanding of physics. So I think if you don't know, this is an assumption. I think if you don't know a lot about physics, like I do, classical mechanics or something like that is really intuitive, right? Like, oh yeah, there's equations we can figure out. If we know these variables, we could figure out, we could drop this ball and you can figure out how fast it's going or where it's going to land. And so without knowing why things are random on a smaller scale, it seems very easy to extrapolate that and go, well, why couldn't you just predict? Is there really randomness? Because we can predict things on this macro scale. Why can we not predict it on a micro scale, right? To use terms that probably don't apply in those senses, but that's kind of where my question comes from. Is why is there randomness once you get to such a small extent? Is it because there are the instruments that we try to calculate it with just interfere with, if you're trying to sense something, right, and you're just interfering with it a little bit, trying to get a read on it, that creates what we call randomness. Or if we could figure out how to calculate it without interfering it, would we realize, oh, it's not really random? We just didn't have enough data.
So yeah, okay. So I guess that answer, or one aspect to that to think about for me is chaos. Cue Jurassic Park theme music. Derek will edit that in. Okay, great. No, I'm just kidding. So I'm sure. Have you heard of chaos, Grant?
Yes, I've heard of it. I don't know much about it.
Me either. I know, but I know the bare bones. And chaos, loosely described, is determinism that we can't determine. Maybe is a good way to think about it. It's like the good physics example of chaos is a double pendulum. So you're familiar with a pendulum, right?
Yes.
So double pendulum is you take your one pendulum and you hang another pendulum off of it. And now you have essentially two pendula in series. And that system is what we call chaotic. And by that, I mean, if you move each pendula to some particular angle and you let the system go, you pretty much can't predict what the path of each pendula, each bob of it would be. And the reason that you can't predict that, though, isn't because it's just fundamentally unpredictable. It's because it is a system of chaos in that if you put it to these two initial angles, and let it go, but then next time you put it to what you thought was the exact same initial angles, but it's really just slightly different. Like you haven't done you can't perceive the difference. In fact, you can go so far as to say, like, you have really good measuring equipment, and even with your really good measuring equipment, all measuring equipment has error, uncertainty in it. Even to that precision, and you let it go again, it would take a different trajectory. The pendulum would move around, because the way chaos works is very slightly different initial conditions can cause drastically different outcomes. And so if you can't measure those initial conditions to absolute precision, you can't predict what will happen in the future. But if you could do it, there's nothing stopping us from actually predicting where it would go.
Yeah.
And there's a lot of times there are particular initial conditions, some special ones that we can set up and predict what will happen.
Yeah, it's that the fundamental laws are deterministic. Like, given the current state, we will be able to predict the future state, assuming in practicality that you could know the state to infinite precision. Even computer modeling, you run up into like the amount of information that can be stored in an initial condition. If you tried to like run a program to simulate it, eventually it would end up being slightly different down the line after so many iterations, because of like the imprecision of the storing of information on your computer. So yeah, that's a way that I guess, randomness creeps in, even though the laws are fundamentally deterministic and there is no randomness in like what should happen to a double pendulum to any mechanical system. The fact that the practicality, the practical limitations of defining a state of that system leads to unpredictability by default. Yeah. And there's varying ways to quantify how chaotic a system is. Like, use the double pendulum, you skip past the single pendulum because the single pendulum isn't chaotic or not as chaotic. But yeah, there's ways, mathematical ways to define the chaoticity, is that even a word, of what's happening. So yeah, it's a fun field of math, applied math.
Yeah. Yeah, and I don't know if that was super clear, but to like kind of make a counter example of like what isn't chaotic, right? It's just, like Derek was saying, a single pendulum. Maybe I should have started there. Is, a single pendulum is defined by its length, is the thing that matters. And if you have a pendulum that's the same length and you move it and you let it go at the exact same spot, it's going to be, and maybe you make the length just slightly different, the period of it will get slightly longer, slightly shorter. It like kind of tracks with your motion. But like with a chaotic system, it would be, if a single pendulum were to be chaotic, it would be like you make it just slightly longer, and now the period is 10 times bigger or something, and then you make it a little bit longer, and now it's 1/10 and it seems like as you kind of go through it that there's no, without further thinking, like there's no rhyme or reason to it, but really there is. You can't measure it cleanly enough.
So that's actually like the core of my question. I just didn't know if I could go, if that was too far into the realm of philosophy. But yeah, like Laplace's demon, right? If you could know everything, right, would you then determine like, oh, there are actually, when things get small enough, they are random? Or would you say, no, it's all calculable. It's just so much data.
Well, yeah. So that was my next.
Random.
That was my next example to give you is, and I used thermo for the example where thermodynamics is essentially, we just talked about this on our podcast, but it's a field. They study kind of what happens on a macro scale to stuff happening in the micro scale. So it's like you have a gas, right? And you compress the gas and you can figure out what happens to like the temperature of the gas, but you don't know what's happening to every molecule of the gas, for instance, right? But the field that studies there's a field that studies the molecules called statistical mechanics. And what they have done is they have figured out by putting a lot of this stuff together that you can actually end up describing how the things change on the macro scale. So they started with the small to explain the big. But even that isn't like, they don't track every molecule or anything when they're doing that of the gas. And I just wanted to know, so I did this math, so Grant's a nursing major. Grant, what is the tidal volume of your breath? Do you know?
Wait, what? What is
the
it?
tidal volume. It's how much you inhale and exhale normally.
Oh, okay.
Putting me on the spot. I think the dead space is probably like 500 milliliters.
Yeah, that's it. That's what I want to know. Yeah. So it's like half a liter. Good job. So just for the sake of simplicity, I said, okay, imagine it's all nitrogen. Air's 80% nitrogen or whatever. We're physicists. Cows are spheres. And so the thing I think that like people, it's hard to do. We've been trying to do this a lot with billionaires to like explain like, what does it really mean to have $1 billion? And it's really hard for people to fathom numbers beyond how big they are. Like it's just hard. So this is kind of one of those problems. So I was trying to figure out how much data would it take to track a breath. And so you have half a liter. If it's nitrogen, you have like 2/100ths or something like that of a mole of it, which, do you remember what a mole is?
Yeah.
6.02 times 10 to the 23 molecules or atoms or whatever, of whatever thing you have, right? So, okay, it's like 2/100ths of that or 2,000, something like that, whatever. It doesn't really matter. So, actually I have it. Yeah, basically in your breath, there are 1.33 times 10 to the 22 molecules of nitrogen in this case. And then I said, okay, when we track particles, especially when they're like, we treat them as billiard balls in physics, the things that we care about are its position and its momentum. And the position has 3 coordinates, X, Y, and Z, and the momentum has 3 coordinates, X, Y, and Z. So that's 6 total coordinates. So I said, okay, let's store each of those as a 32-bit number, which is kind of a standard practice. So then that leads to, if you store that number of molecules with those 6 32-bit numbers for each molecule, that is 20 trillion terabytes of data. and just because 20 trillion is still a big number. I still haven't made this real, I don't think. I kept going. That's, let's see, 672 billion 30 terabyte SD, like what's in your laptop. So then the next day I said, okay, that's still not, I still don't have enough info there to help. So I said, okay, what's the volume of an SSD? And how much if you were to put all that data on SSDs, what volume would that fill? And the answer is 67 million cubic meters. Okay, still not based in reality yet. What is the volume of the Empire State Building? It's 1 million cubic meters. So the data in your breath would take up 67 Empire State Buildings worth of 2.5 inch hard drives, 30 terabyte hard drives.
Nice. That's even making assumptions to simplify things. Meaning, like, we're just talking about balls of nitrogen molecules, not worried about the interaction information or the quantum stuff going on inside the atoms themselves. So it can keep going. Even more information is available, but we have to stop somewhere.
All I can think of as you explain how much data that is like a simulation theory. And then how much, but that's neither here nor there for this conversation.
Yeah.
So basically Laplace's demon is like so outside the realm of possibility, even considering one breath worth of information, that it's essentially not irrelevant. It's a philosophical tool to think about things, but we just don't worry about it. Like not possible to gather all the information about position and momentum of all particles and draw conclusions. But in theory, if you could, yes, everything is deterministic, except I think your third point, Zach, is going to come up. Our laws of physics are deterministic. Given some state, you can figure out where it was, you can figure out where it's going to go in the future to infinite precision if you define the initial state infinitely precisely. But let's hear number 3, Zach, because I think that's going to ruin it.
Yeah, okay. Number 3. Oh, and just to be clear, though, Grant, because I kind of said this, but I just want to rehash it. A breath takes up that much data, but like the cool thing with physics is that a lot of still the information that you really care about on your day-to-day life, you don't need all that to like figure out what's going to happen, right? Like, what is the volume of your breath, or like, what is the temperature of it? Or, it's kind of weird talking about just breathing it out into the air, but for physics, you breathe it into a sealed cylinder that you then can compress and do work on it or something like that. But like, you get really far by looking at these kind of state properties of the collective, of the group, instead of like each individual thing. Okay, so the last thing, this is going to ruin everything as far as we know it. So far, I think we've said pretty much with infinite precision, you can know, but infinite precision is just
impossible.
Infinitely hard. Okay, so the last part is quantum mechanics. This is where it all breaks down. It's where there's true randomness as far as we can tell. And we have had podcast episodes on this, and maybe we can rehash some of that a little bit, I was thinking. But basically, like, I think the easiest example, the quintessential example everyone turns to is the double slit experiment. Are you familiar with the double slit experiment?
No.
Okay, so it's where you take something like a photon, or maybe an electron is a little more, tangible for you. I don't know. So you take one electron, and you fire it at a pair of slits, like a piece of metal with two vertical holes in them. And then on the other side of the slits, you put a detector that detects where the electron landed. And you fire one electron at a time. I'll just say one electron at a time, whatever, that's fine. And you do this, a billion times or a trillion times or whatever. What you see on the other side, if you were to imagine baseballs flying through a slit, right, would be two vertical lines that kind of match the shape of the slit, right? They're not going to like go in crazy directions. They're just either going to go through the slit or they're going to hit the panel and not go through the slit. And that's kind of all you get. But with quantum, what you actually see is a wave pattern, like as though two waves went through each slit and the waves interfered with each other and then hit the detector. And you see this varying intensity pattern across the screen. So it'll have some bright spots, some dark spots, but it doesn't look like two slits is the key takeaway there. It kind of looks more like there's a bright spot in the middle, and then it gets dark, and then it gets bright again and dark, and as you get away from the middle type of thing. And fundamentally, we don't have a way of predicting where that electron beforehand is going to hit on that screen. So it can hit any of those bright spots. Basically, a bright spot means more electrons hit that spot than a less bright spot. Dark spot means no electrons hit that spot. We can tell you kind of the group behavior. We can tell you a lot of electrons hit here, a lot of electrons did not hit here, but we can't, if you fire an electron beforehand, I can't say that electron is going to hit this spot here. Like, I just can't do it.
So there's your randomness built into the laws of physics, because the laws of physics predict exactly where those bright spots are, but we can't say this electron is going to hit that bright spot. Like, that's not possible.
Can we not do that, or can it not be done?
Whoa, Albert Einstein.
It's worse. It's worse than that. It's not even that it doesn't happen. Like the rules of quantum mechanics say that both things happen at the same time, meaning ask the question, where will the electron hit the screen? And to do that requires the electron to go through both slits in our current universe. Like the past history of that electron was that it went through both slits. Now, if we would have phrased the question differently and said, which slit did the electron go through? And by asking that, we try and answer it by measuring it. It fixes it to go through one of the two slits. But before we ask which one and we check which one did it go through, the physics says it went through both. And the physics at random takes that, like, I'm going to use the technical term, the wave function, and it interferes with itself, and then it hits the screen somewhere with the probability dependent on how that wave function varies with space along the screen. And so the randomness shows up because the fundamental laws of physics for that electron are a probability distribution along the screen with like a 10% chance it's here, 45% chance it's there. We can get those probabilities. Those probabilities are deterministic in that we know what they are based on the formulas, but just because we know the probabilities doesn't mean that the actual answer of like, where did it hit on the screen? That's not determined by the laws of physics.
Yeah. And so Albert Einstein asked the same question you did. He said, I think it's just so there's two fields of thought, even today. And just for reference, Albert Einstein and Bohr and everything were arguing this in the 1920s. It is the 20s now. Jeez.
The other 20s, the last 20s.
Yeah. Bohr said, no, this is just, you can't do this. This is just the way the world works. And Einstein thought, I think maybe you just don't know enough, that there's some information that you could dig down deeper and figure this out. And basically that would mean that there's something that they call the hidden variable. There's something that we don't know exists that we can maybe measure to determine where, like for the electron, if we could measure that before it hit the screen, we would know where it's going to land after it passes the slits, or before it passes through the slits, we could know where it will land on the screen. But then is it the 50s, 60s? I don't know when Bell came along.
Something like that.
Bell came along and created this theory that said, okay, if hidden variables exist, we expect this outcome to happen.
He gave an experiment to test whether that's true or not, whether or not hidden variables exist outside of what we currently understand of physics. And he says, if there are, we can run this experiment and see certain things.
Yeah, and he didn't say like we can measure, we'll figure out what those hidden variables are. Just if it exists, if there are hidden variables, we expect this outcome, or if there are not, then this outcome. And we did the experiment, and it turns out that there are no, and now I'm getting more technical here, what they call local hidden variables. Like there's no stamp on an electron that says, I will do this. I'm going to go, I will do this, that we can measure. And we've proven that. Have
shown that to be true. Yeah.
Yeah.
Yeah, and the double slit is a great example of the quantumness of physics for particles. A simpler one that's like, just answers the question, is there anything truly random? Is the decaying of a nucleus, an unstable nucleus? Like, it is truly random that it'll decay at some point. We can't predict it. We can predict the likelihood it's going to decay. We can predict if we had, N atomic nuclei, how many would decay per minute or something like that, just as an average. Again, it's all statistical, and we know what the probabilities are, but we can't say definitively, like, this atom will decay at 10:47 a.m. on Saturday. And it's just a random chance every second of, is it going to happen this second? I don't know. Is it going to happen this second? I don't know. But each second has a likelihood that is predicted by quantum mechanics. But the fact that it happens is not predicted. Quantum mechanics is fundamentally deterministic, which sounds like randomness shouldn't be allowed, but it is. So it's interesting that you have a theory that explains experimental results very, very well, that is completely deterministic, by which I mean, given an initial condition, you will know the state's state at some later time, the system's state at a later time, fully determined by quantum mechanics, 100% explained, totally good. The problem is the state's definition is a list of probabilities of something happening. So there's your randomness by saying deterministic probabilities. You know exactly how those probabilities will change over time, but the end result of what actually happens at the end of doing some experiment, checking on something, sometimes called the measurement problem. We know exactly what the probabilities are, but the second you check, it collapses down into one of those results of the experiment, which had a probability of occurring, but which one occurs is not determined by quantum mechanics.
And additionally, though, no, I'm not going to add this yet. I don't want to convolute.
I'll convolute. I was going to add that the interpretations of what that means vary. Different people interpret what the ramifications of that are in different ways. One of the ways, and I'm going to say it's the most popular way with physicists right now, is the many worlds interpretation of those results, meaning if there's a chance of going in the left slit and the right slit, and quantum mechanics tells you the odds of each one happening, and it's a mix of both of those things until you ask and measure which one did it go through. The many worlds interpretation says there's a world where the particle went through the left slit, and there's also a world where the particle went through the right slit. And until you check, you don't know which world you're in. And in fact, you're in the world that's the unchecked world. So you let it go through. It actually goes through both. That's the world we're in if we let that happen. If we check and see it in the left one, we are now in the world of the left slit as the answer. And you continue on in that world forever. And like the worlds have just split. All of them are happening, and we just find ourselves in different ones along the way. So all of them are determined by quantum mechanics, and they're fully explained deterministically based on initial conditions. Totally understand all of that. The weird thing is that there are all those worlds, but they're all deterministic. They're all determined and not random. But which one you find yourself in is the randomness.
So just to make sure that I'm tracking.
You got all that, right? We don't.
I'm pretty sure I did. It went slightly different than I had expected. So I was like, oh, wait, hold on. Let me just double check here. So in theory, it is deterministic, but also we may, according to the many worlds interpretation, just find ourselves in different universes, would you say?
Yeah, I mean, you could pick your word.
Planes of existence.
Yeah.
And we have no idea which one we're in, and that is the randomness.
Yes.
Or which one we will end up in. Maybe we know which one we're in because we measured. Found out we're in the slot, the world where the electron went through the left slit.
Yep.
But beforehand, we couldn't tell if we were going to be in the world where it went through the left slit or the right slit.
Right. That's right. So the likelihood of where you end up is determined 100%. How many versions of us are in the left slit versus the right slit? Totally determined. But there's no way to look forward in time and say which world will we be in the future. Which one of us will be the one that goes to the left slit? And to be fair, I just brought in a word I shouldn't have, us, like the people, the things. They all are existing at all times. And I mean, Zach went through the numbers for the molecules in a breath of air and then the information required. The amount of just numbers, just the biggest number possible, is that splitting of the universe that many times. Like literally, I'm talking about slits left and right. That's very clear, 1 and 2. But like everything you're touching around you has like a chance of happening in some way. And like every version of that is occurring at all times, constantly splitting. Every molecular interaction in your body, in your brain, on your desk is occurring at once. And we keep forking and splitting. And how many universes are there now? It's a question of whether it's infinite or not. And I think there's implications of that. Like it could be an actual infinite result, but we don't actually know. So
also, I want to state that many worlds interpretation is just an interpretation. And there's not like hard, concrete evidence where you've reached across to the right slit aisle and been like, hey, you guys saw right slit, right?
Yes, that there's no way to verify that as of yet. And there's other interpretations of quantum mechanics which have other meanings that don't lead to the splitting of worlds. I've gone deep into Sean Carroll, who's a physicist and pop science writer, in for other ways, but he talks about many worlds and he's a big proponent of it. And his reasoning is it is the only interpretation that doesn't add anything to quantum mechanics. It just takes what quantum mechanics says at face value and says, don't even bother with anything else. There is a wave function of everything and it behaves according to quantum mechanics as we understand it. Don't try and add other things that happen like a pilot wave or the measurement problem. Like all those things are adding on top of what we understand as quantum mechanics. Many worlds is the one that's just like the bare bones, take it at face value. Don't try and do anything special. And it's weird. The end result is weird, but that's his reasoning, is because it doesn't add anything.
Very Occam's razor.
Yeah. Well, a counter to it is Occam's razor is like, it's not that simple because it just feels so wrong. Like it's not the easiest answer, therefore the right answer. But yeah, it is that, and that it doesn't add anything. So why not just believe it? Yeah. Question for the table. If all of physics is deterministic, meaning given a perfect initial condition, meaning given if Laplace's demon could exist, and it obeyed the laws of physics, which knew everything in the past, everything in the future, because it followed the rules. Are we deterministic? I just went into the outside of physics area, but that's where it leads, and it hurts my head to think about. And yeah,
I don't know as much physics as you guys. I would call myself a hard determinist. I totally, absolutely. I think, yeah. I think if you could say there's not randomness and Laplace's demon could figure everything out, that's where I would go.
I don't know where I stand, honestly. It's definitely like into philosophy land that I'm not comfortable with, but I tend to agree. Like if Laplace's demon could exist, then yeah, everything is deterministic. But does that mean we don't have free will? It's like, remove the knowledge, like take Laplace's demon, infinite knowledge of everything, and then start chipping away and leaving some unknowns. And then I think we're left with what we would consider free will because we're unable to know everything. But clearly I can hit end on this call just by choice and say bye. But you don't have a choice in that. But yeah, it's interesting. Like I don't know the answer.
Yeah. I mean, I don't know either. I know there's a lot of really interesting studies of things going, like, if they put you in an fMRI machine and look at your brain while you're making a choice, for a lot of choices, they can tell you what choice you're going to make before you know which choice you are going to make, because they can see it in your brain happening before your consciousness recognizes that this is your choice. So that, that's kind of weird and interesting. But I mean, I think even Laplace's demon, though, right? Like Laplace's demon doesn't know which slit the electron went or is going to go through. And
yeah, so I should say the free will argument of like deterministic physics is get rid of the random chance of quantum mechanics, because that just throws it out the window. But it's a different thing to say because of the randomness of quantum mechanics, we have free will. I don't know that that's true, but it's possible to have randomness and free will, possibly.
Yes. So I guess what I was going to say is because there are people, I haven't read Penrose, but I know Penrose believes quantum mechanics is like a basis for consciousness. There's a professor at UCSB that studies is theorizing about these things called Posner molecules, which are in your brain, and that those might be a vector for a quantum mechanical consciousness. And the point, I don't know if their goal or not is to say free will exists. I'm not sure that they're doing that or not. But the point, I think, is to say that there might be some unpredictable aspects to what makes consciousness. And then in that case, maybe there is more free will like things than we think, but I don't know.
I think as soon as you, so I think if you take Laplace's demon, then you could figure out, if you know all of the data, you could figure out where everything's going, you could track everything. I think then you would fall into the realm of hard determinism. I think as soon as you start taking away known variables from that, in fact, I could be wrong, but I think if you take away one known variable, just have one thing that you don't know, then I think you open up the realm of free will, because then you just don't know. But I think there's also an argument to say is that randomness is not free will.
Yeah. It's, I don't know the philosophical logic for why that's true, but I think it is true that you take away one and then free will exists. It feels very God of the gaps for like atheism arguments. Like, oh, we don't know that, therefore it's God. And it's like, we don't know this, therefore it's free will. There must be a better argument for why that's true, but it feels not right. But I think it is philosophically, people have logicked through that reasoning. There's a thing I just was looking up before hopping on this call called compatibilism, where free will and determinism are fine together. Like you can have both. You can have deterministic laws of nature and also have free will of people's actions. And the premise is no one has control over the past and no one has control over the laws of nature. And the past and laws of nature determine the future. Like take those two things as assumptions. And I'm pretty comfortable with both of those as assumptions. And therefore no one controls the future. Since no one controls the past and no one controls the laws of nature, which determine together the future, no one can control the future. So I think that is fine. You can have determinism and also free will. By that, I mean, like, you can't control the future. The future isn't determined. I might have just talked myself into a circle there. So apologies for those taking notes and being like, wait a minute. Yeah, it's similar to the thermodynamics concept that we were talking about earlier of the dynamics of the molecules themselves are completely understood using billiard balls as just like things colliding in the air around us. Totally deterministic. But there's macroscopic emergent phenomena like temperature and entropy that aren't, well, entropy in particular, not so much. Like, given the initial state, we know exactly how things will evolve. And entropy ends up bringing in kind of a statistical way of thinking about the evolution of things. And I think in particular, the determinism works in both directions of time, meaning you can play a video back of billiard balls colliding and then go in the other direction, and it's explained through the same rules of physics. But entropy is not. And so that introduces this asymmetry of past and future things that are allowed in physics, and that might be a place where free will comes in that there's basically the second law of thermodynamics means that we have free will. That's the biggest leap of therefore I think possible. But I think there's something there. I don't know what it is, but if I had to guess, it's somewhere in that realm of thinking about things where we introduce these gaps of free will and also time, the asymmetry there, which is going to be a later episode. I'm finishing up that Sean Carroll book which is super interesting. And I feel like I could talk an episode worth of content through right now, but I want to finish the book to make sure I didn't say something totally wrong and then find out in a later chapter, like, oh, this is actually not the correct way to think of it. So, well, cool. I think that was a fun conversation.
Yeah. Do we answer
thoughts?
your question? Do you have any other things you want
to? Yeah. So can I read you my takeaway and then you just like double back and tell me if I interpreted correctly or not?
You're taking notes?
Heck yes, I'm taking notes.
Wow.
I gotta.
What a good student. Now I'm nervous. I've never had somebody think back. I guess students do that all the time, but yeah, let's hear the takeaways.
I won't say everything because I had you are very intelligent fellows. I had to take notes to track the conversation because I'm out of my depth. So to the initial question, if we were to say like Lovelace's demon is a thing, we could. In fact, the only thing that is kind of left unanswered about that is like radioactive decay. I am not totally sure if that we said that was random, but I don't know if you can know every element. Would that still be random?
I think the answer is yes to that.
Yes. Okay.
Yeah. That I think that falls into the hidden variables sort of thing, where there are just things that it seems like right now, of all the knowledge that we have, who knows what theories will come in the future, that there's no way for us to know what, like there's no stamp on a particle that will ever say I will decay at this time. Like that just fundamentally doesn't exist. So because of that, some of these things are truly random, like that you can't possibly predict it.
Mm-hmm.
I think Zach answered it in the very first with one word. He said yes.
Exactly. So the fire pit example, the person describing, like, if I knew everything about the atoms that led to the fire, the flame coming up out of the wood, would I be able to explain in perfect detail the exact motion of the flame? And I think the answer is yes, assuming there's not a huge source of radioactivity underneath the fire pit or something like that. But like you could, in theory, with Laplace's demon.
But in practicality, there's randomness because we can't calculate. We don't have that much data. Right. And there's really not a need for that much data. We don't need to fill 67 Empire State Buildings to calculate all of the nitrogen molecules in the tidal volume of one breath.
Yeah.
Yeah. And like, I mean, if with that flame one, like that one just goes like, it's like the many worlds. It's just so, it exponentially just grows with the amount of information that you need. Because I was thinking about it, like, okay, so you have a flame, or you probably need to know like where the energy first started on the fuel, how much oxygen is around it, the state of all the oxygen, because that's going to have to interact to create the combustion reaction, and then maybe a oxygen molecule is coming towards this spot of energy to create a reaction, but a cosmic ray comes flying out of nowhere, hits it and breaks it into 2 oxygen atoms or something. So now you need to track where that cosmic ray is. And that cosmic ray came from a galaxy 500 billion years ago. And so from a star, you need to know what was going on in that star. Like it just ramps up super quick.
And I think what you're highlighting is back to the quantum mechanical many worlds thing, is like there is a wave function of the universe, and it's like literally all encompassing. Everything is explained by this mythical universal wave function. But for that exact reason, because everything is so interconnected at some level, we do need to take everything into account. But quantum mechanics explains perfectly how that wave function behaves. It's just a massive amount of information that's wiggling around. Sean Carroll, again, I guess I'm just like fanboying it up today with Sean, but he has a good, interesting take on the reversibility and the second law, where he says, take all the air in the room and squeeze it into a balloon, like a little ball in the center of the room, pop the balloon and let all the air just expand out. And that is explained through the dynamics of the particles interacting with themselves, slamming into the walls, everything is fine and dandy with billiard ball mechanics. And the second law of thermodynamics, totally fine. Works both in both those cases. But play the videotape backwards of that occurring, and it's just, we don't see that ever happen. We never see all the air in the room collapse into a little balloon-sized sphere in the middle of it, and then we asphyxiate out in the corners. It just never occurs. So why is that reversibility broken for that behavior when the fundamental rules of the billiard ball collisions is totally reversible? It should be fine, but we just never see it. And you said something, Grant. I think you said it a second ago about observing things where we look, not the quantum mechanical observations, but it gets kind of to the chaos talk where, like, if we were watching the gas molecules and we had that set up perfectly, Laplace demon knowledge of the molecular momentum and position of everything in the room, and set it up exactly right and said, go, we would never see them collapse back, because just the act of looking, a photon hitting one of them would send it off and not let it come back to that perfect exact situation, because in the second law of physics, it's just so unlikely to occur. It's just so rare in terms of all the possible positions and momentum of all the gas molecules for them to exist in a little sphere in the middle of the room, that looking at one of them on its way back to that position messes it up enough through chaos theory, you could say, that it wouldn't go back to that exact configuration. So I think that's an interesting split on the time decision, but also, yeah, why is it equally likely for things to collide as expected in forward and backwards in time, but not necessarily an ensemble collection of these huge numbers of particles? We just don't see it happen.
One word I wanted to bring up, Grant, just to introduce to you that we haven't said yet. I don't know why we haven't said it, but is this term called superposition?
We talked about it, but we didn't say the word. But yeah.
Yeah, exactly. Yeah. So yeah, superposition. Well, there's like multiple meanings of that word, but in quantum mechanics, it's a combination of being in like multiple states at the same time. So it was like back when Derek was saying, we look at the screen and we see the electron, we see that pattern. The only way for that pattern to have happened is for the electron to have gone through both slits at the same time. That's a superposition of going through the left slit and the right slit at the same time. And it's not like it's we don't know how to explain this, we're using this word. It's like, no, it's real. It's a real superposition is like a state of being. You can be in a superposition of states. Like it's and so I feel like that's just something that a lot of people aren't comfortable with, is saying that, light took two paths at the same time, or did this thing at the exact same time. But that's a superposition. That's a thing. We can deal with it. We work with it quantum mechanically, and it's fine. It's fine,
and it actually ties how the double slit experiment ties into the radioactive decay randomness, because that is a superposition of decayed and not decayed in quantum mechanics. So those are the two things existing at the same time until you have a little Geiger counter go click. We don't know if it's decayed or not. So if we don't have a Geiger counter, we're not checking. It's in a superposition of both of those states, which we haven't talked about Schrodinger's cat, but that's why he brought in the cat in the box with the radioactive thing, is because we know the radioactivity is a quantum mechanical process and it lives in a superposition of decayed and not. Let's lead to something macroscopic happening based on the results of that. And look how this is not enough information. Something's wrong is what he was trying to say. So it's the superposition principle of quantum mechanics that leads to that double slit interference pattern, but also the Schrodinger's cat with the decaying nucleus inside the box. So that's the randomness of quantum mechanics, in that before you check, we know all the probabilities, but they're both happening at the same time. All results are happening at once until you ask which result happened, and then you say, okay, it's that one. But you got a roulette wheel worth of chances with particular odds for red or black or green, which quantum mechanics gives you perfectly.
Cool. All right. So I guess I just want to make sure we answered or left you more satisfied than dissatisfied, Grant.
Yes.
Sorry, no refunds. Satisfaction not guaranteed.
Well, now I'm left with accepting superpositions at the end of that. Like, it's counterintuitive to me that I'm like something can be in two spots at the same time. That's what it seems like. But I accept that because we live in a world where counterintuitive things happen.
Yeah, I mean, there's the quantum mechanical interpretation summed up as shut up and calculate. And that's what I am trying to advocate to you right now is that's just what we see when we do experiments. We see superpositions being real things. Don't question why they're there. Don't try to explain them. Just they're there. Shut up and calculate. Like, just it's a fact of life. Deal with it.
The calculate thing is important because we keep harping on the fact that quantum mechanics does give you the exact probability every time to the perfect results. Like, what's happening in quantum mechanics probabilistically. But that's the calculate part. It's like, just shut up. You can calculate the probabilities. It's always going to work. But don't ask what happens when you actually do the measurement, because that's just interpretation. Cool. So yeah, like most good eye-opening lectures in class, I hope you leave with more questions than you came with.
Yes.
Good.
I think after I soak in everything and I interpret it, I'm a man of many questions. I will probably have a lot of follow-up questions.
Cool. Well, I enjoyed this. I think it was good to have a lay person on the podcast. So hopefully we can have you back in the future, Grant, and we have a continuing segment of Grant Asks.
Yeah, absolutely. I'll try to come up with a question that can not be answered with a yes.
Yes or no questions are not.
No, I mean,
well, cool. Yeah, thanks. It was great to meet you, Grant, and hope to have you back at some point in the future. If the laws of physics conspire, I think you don't have a choice. It's going to happen one way or the other. You don't know yet, but it's determined.
Depends on.
Yeah. I guess I hope we land in the world where Grant joins us.
Yes.
Thank you guys for having me. It's been a pleasure. I would love to come back.